Hello students, welcome back. Today's lecture is going to be Signal Transduction Part 5. And let's just start where we left off last. Okay, we talked about this entire signal transduction cascade, and we stopped with the influx of calcium. But we still didn't see, well, how does that influx of calcium lead to greater contractility of the heart? So we're going to come back to this in actuality. And then we talked about how the heart actually works. There's a sinoatrial node that paces the heart. It paces specifically the atrium, and that wave of depolarization reaches the atrioventricular node, and then it sends its signal out through these Purkinje fibers, and then you get ventricular contraction. And there has to be a delay. Atrial contraction, fill up the ventricles, then ventricular contraction. So you don't want it all to happen at the same time. Fill the ventricles, push the blood out. Fill the ventricles, push the blood out. And so there has to be a delay. And the tissue that's responsible for that delay is the AV node, along with the bundle of His. And the Purkinje fibers work in a way as to close the ventricles from the bottom, so that the blood goes out the top of your ventricles. Okay? Hope that makes sense. In order to increase the heart rate or to get greater contractility, you have sympathetic nerves that release norepinephrine on the sinoatrial node, on the AV node, and even on just regular cardiocytes. And to lower your heart rate, you have the vagus nerve, which comes in, releases acetylcholine, and slows the heart down. It really doesn't lower contractility so much. Well, I guess it could, but mainly it just slows the heart down. Okay? And now, and the last thing we're going to talk about now is, how does a heart cell, under normal circumstances, how does a heart cell contract? What is the physiology and what is the biochemistry of just normal contraction? No vagus input or no parasympathetic input, no sympathetic input, just a regular heart cell. Okay. The first thing we do is we get depolarization of the cell. And so, starting out, your heart cell has lots of sodium on the outside, very little sodium on the inside. And so the heart cell receives a wave of depolarization from, let's talk about this. You get a wave of depolarization coming into the heart cell. From where does that wave of depolarization come? What tells that ventricular cell, it's time, you need to depolarize now? From whom does it get its signal? The AV node, exactly. And so the AV node comes in, and it tells that heart cell, okay, depolarize. Tells that ventricular cell to depolarize. That ventricular cell has sodium channels in it. Those sodium channels open up, and it floods the inside of that heart cell with sodium. Also in the membrane, you have these calcium channels. Those calcium channels sense that there's depolarization, and then they open up, and they allow calcium to come into the cell. And this calcium is called trigger calcium. This calcium goes to the sarcoplasmic reticulum, activates the sarcoplasmic reticulum to release its store of calcium. And so then lots of calcium comes out of the sarcoplasmic reticulum. And we call this calcium the calcium spark. And now we're going to find out today, bless you, how does this calcium lead to greater contractility? Or how does this calcium, not greater contractility, excuse me, how does this calcium lead to contraction of the heart cell? Does everybody see where we're going? Excellent. Very good. So now we're going to have here, I'm going to actually put this on a new layer. We're going to have a contractile unit of our heart cell. Okay, this is going to be our sarcomere, and extending from the side, we're going to have actin filaments. Here's actin, actin. I'm going to label all of these soon. Actin. And then right in the middle of that sarcomere, you're going to have the thick filament. And on this thick filament, we're going to have myosin, the heads of myosin. Okay. So we have a sarcomere here. I'm going to go ahead and label a few things. This entire structure is called a sarcomere. That's a contractile unit of skeletal and cardiac muscle. A sarcomere. And so there are lots of these sarcomeres just connected to one another. And when these, I can just show you here. Before I explain anything, I need you to understand what needs to happen. Okay? Okay, here's our sarcomere. Now, what's going to happen? In order for this heart cell to contract, you need to pull these proteins in. These proteins in the sarcomere need to overlap one another to make the heart cell shorter. And when every heart cell gets shorter, let's say they make up this opening here, and this opening is the ventricle. When those heart cells and those proteins overlap one another and the heart cells get shorter, it's going to start squeezing in on the ventricle. And then when the ventricle squeezes itself, it's going to push the blood out. Does that make sense? So you need for these proteins to overlap one another. And so what has to happen? So let's imagine that I don't know if we can see. Would you zoom out just a little on that? Zoom out just a little. And would you come up, please? And would you come up, please? Okay. You all stand up here with me. Okay. And just make sure you can see all three of us. Okay, you stand there, okay, and you stand on this side, okay. Okay, I'm going to be, can you see all three of us? Okay, I'm going to be myosin, I'm going to be the thick filament, and each of them is going to be actin, okay. Now you make sure I'm going to spread them out, okay, you spread out, okay, very good. Okay, now hold your arms out. Now this is actin, I'm myosin. In order for me to shorten them, I'm going to have to pull them in. I pull them in. And then when they shorten, and you have to just imagine, this is a very long protein. It goes the entire length of the cell. And so the whole cell is going to shorten. And so we have to overlap. So y'all go out again. Go out again. Hold your arms out. And now, this time, I'm just going to hold my arms here. It's going to be like, the actin doesn't, the whole part of the myosin doesn't move, just a part of it. So I'm going to do this, and you all come in. Just come in. And so those actin filaments those myosin filaments keep pulling on the actin until it comes in. But there's something blocking that. And so when we remove that something that's blocking it, then you get contraction. Does the concept make sense? How you make contraction of any muscle cell. This can be a heart cell or a skeletal muscle cell. Make sense? Okay, very good. Thank you all. Thank you all. Okay, go back out. Zoom back in on me. Okay. And now let's see what's going to happen. Okay, so this is going to be part of our sarcomere. So what's going to happen? It's going to shorten. So when those myosin filaments pull on it, it's going to cause this to shorten. I'm just saying the same thing another way. But does that make sense? Okay, very good. Now, before we continue, let's just label a few things. I'm going to put my label on another layer. So, let's see here. This thick filament is what protein? Myosin. So this is myosin. Okay. This thin filament is which protein? Actin. on the actin filaments, there is a place where the myosin binds. So there's a site on the actin filament where the myosin binds. Okay. I'm going to actually make my myosin here just a little smaller so. Okay. Let me just find myosin here. Doesn't want to be found. There it is. Okay, very good. Okay, there's my myosin. I'm going to put it back in place. But now I'm going to make it a little smaller because it's too big for what I need it to do. So I'm going to make it thinner. Okay, I'm going to make my myosin just a little thinner so I can do something because I need space. Especially here. I'm going to move it down too. Okay, there's my myosin. And there are places on the actin. Whenever that myosin head touches the actin, it's going to get contraction. So when you don't want contraction, you need something to cover up those myosin binding sites on actin. Does that kind of make sense? So let's put something there to cover those actin binding sites. So we're going to put ourselves a protein here, and this protein is going to cover those actin binding sites. And so as long as those proteins are there, as long as this protein is here, you don't get contraction. And so right now, let's just worry about the top half. Right now, this cell cannot this cardiocyte cannot contract because the myosin binding sites on actin are covered up. And the protein, well, we aren't even going to name it yet. Just going to get the concept first. Attached to this protein is another protein here. There's another protein attached to this protein. And so now when you want contraction to take place, what happens, this calcium from our calcium spark, let's see if I can find one of them. Okay, good. I'll just take one of these. This calcium from the calcium spark comes over and binds to this protein. And when it binds to that protein, then this second protein, it binds to the second protein, it pulls this protein away. Go back in. It's giving me two of them. I don't want both of them. Sorry, you all. Okay, we don't need this one. We just need this one here. Okay. Then what happens? It pulls. And where's calcium? Hope that's it. Then it pulls this protein away. Now myosin can bind to actin and gives you contraction. And so the whole reason that we need calcium is to move that blocking protein away from actin, and once that blocking protein moves, then we get contraction. And that's how a heart cell contracts. Does that make sense? Exactly. But when this protein is here, let's say you put that protein there, now you don't get contraction. So during systole, when the heart is relaxing, so when the heart contracts, we call that systole. We call that systole. When the left ventricle contracts, we call that systole. And when the left ventricle relaxes, we call that diastole. Diastole. And so you have a systolic blood pressure when your ventricles are contracting, and then when they're relaxing, we call that diastolic blood pressure. And so during let's do diastole first. I'm going to put my calcium up here so I can see both of them. Okay. So during diastole, your calcium is in, well, this is not really accurate, but during diastole, all of your calcium is trapped in these vesicles here. But and your actin and your binding sites, your myosin binding sites on actin are covered up. And so when it's time for your heart to contract, this happens very quickly. The calcium is released. Then the calcium binds to this red protein, which we'll name in a second. Then the red protein is going to pull the blocking protein away. Myosin is going to go up, pull the proteins in, and your heart contracts. Now it's time for your heart to relax. Now the calcium is going to go back into its reservoir here, and now this protein is going to go and cover the actin back up. And so this has to happen 60 times every second. Calcium coming out, binding to the protein, moving it out the way, actin binding, pulling it in. Then there are pumps here that pump the calcium back inside. Then the protein goes back and covers up the actin binding site. So that has to happen very quickly. And that's how you get contraction of your heart cells. Kind of makes sense. Now that we have that, now I have a question for you. Okay? And so then your calcium goes back in here. What if we could come up with a way to, let's see here. I'm just going to put, what if we could come up with a way to put more calcium? If we could come up with a way to get more calcium, let's see, calcium coming inside. We come up with a way to get more calcium inside the cell. If we get more calcium inside this cell here, if we could do this, then I'm going to get rid of this one. Then during diastole, when those pumps put this calcium back into these chambers here, say get the calcium into these chambers, now you're going to have more calcium stored in these chambers. Make sense? Now what's going to happen next during the next systole? The next time the left ventricle contracts, what's going to happen? Now even more calcium is going to come out. This calcium and the extra calcium. Now all of that calcium is going to bind to these proteins here, and you're going to get a lot of these proteins getting out of the way. Now when the heart gets ready to contract, now you're going to have greater contraction because there are more binding sites for the myosin to bind to. Does that make sense? And you're going to get greater contraction. And so now we're going to figure out, well, what do we know of that can increase your calcium level in your cell? What do you know of already that can increase calcium level in a cardiocyte? No, not vitamins. Norepinephrine. Exactly. Remember, let's go back now. Now it should all come full circle. So let's get rid of this for a second. And we can see here, if epinephrine binds, if you get sympathetic activation here, then what's going to happen? You're going to end up having more calcium in the cell. And that more calcium is going to lead to greater contraction of the heart cell. That's why if a large dog is chasing you, your heart is going to beat more strongly, because the epinephrine or the norepinephrine is going to increase the amount of calcium inside your heart cell. Does that make sense? The whole point of everything before this is for that fact to make sense. Do I need to say it again? Okay. Now, let's do this part first. Normal contraction of a heart cell. To get contraction of a heart cell, calcium has to come in. Trigger calcium has to come into the cell. This trigger calcium is not used for contraction. It just activates the vesicles so that the vesicles can release calcium. When the vesicles release the calcium, I'm going to kind of get rid of this one for right now. I do not know why that's not working. Oh. Okay, when those vesicles release this calcium here, let's see if we can find that calcium. Which one is it? It's got to be this one. Okay, there it is. When the vesicles release this calcium is going to bind to this protein, and when the calcium binds to this protein, then that protein is going to move the blocking protein out of the way. Now you're going to get contraction. That's during ventricular contraction. Now there are going to be pumps that are going to pump the calcium back into the vesicles. Now this protein is going to go back and block the actin binding sites again. Now you're going to get relaxation, or ventricular relaxation. The strength of the contraction depends on how much calcium there is to move these blocking proteins out of the way. If you only have a little calcium coming out of those vesicles, then you'll have a mild contraction. But if you have a lot of calcium coming out of those vesicles, then you're going to have a strong contraction. One way to get more calcium into those vesicles is to put more calcium into the cells. And so that's what norepinephrine does. Norepinephrine brings more calcium into the cell, and then those pumps put that calcium into the vesicles. Now, when you on the next ventricular contraction, you release the regular calcium and the extra calcium. Now the extra calcium is going to cause even more of those blocking proteins to be moved out of the way, and now you're going to have stronger contraction. Does that part make sense? Gonzalez, make sense? Now,
so the calcium that comes into the cell, where it says the trigger, does that actually go into the chamber?
no, it doesn't go.
Already in the chamber?
No, it doesn't go in the chamber. It just goes to the outside of the chamber to tell the chamber to open up. And when that chamber opens up, then it releases its calcium that's trapped there.
So all of the calcium that's in the chamber just keeps getting recycled?
Exactly. It just keeps getting recycled. But if you could come up with a way to get more calcium into that chamber, then the amount that's coming out is going to be more, and you're going to have greater contraction.
Does it stay there forever, or can you lose?
Eventually, like if it's doing a sympathetic response, what's going to happen if there's let's go here. And so what epinephrine is going to do, it's going to bind here, and you're going to eventually get more calcium into the cell. And so you have to think, calcium has got, some pumps are going to be putting the calcium into the chamber, some of the pumps are going to be putting the calcium back outside. But the calcium that goes into the chamber is going to make the contraction stronger. If epinephrine goes away, eventually that extra calcium is going to be pushed back outside. And so then your heart rate is going to go back to normal. There are going to be, just like there are pumps that bring the calcium inside, there are going to be pumps that are going to put the calcium on the outside. And eventually, because there's a lot inside the cell, that lots of calcium that's inside the cell, it can go one of two ways. Lots of it is going to go into the pumps to increase contraction, and some of it is going to go to the outside. So eventually, those outside pumping calcium channels are going to just eventually pump those out until you get back to normal equilibrium. No, they're still working, but because they're putting so much calcium in. Think about it this way. Let's say you have epinephrine comes along, and now you have, let's go here. Think about it this way. Let's say in this pump here, or in this, think about it this way. Let's say within this calcium channel, this calcium trap here, this calcium vesicle, there are 100 calcium ions. Okay? There are 100 calcium ions. Now, let's say epinephrine comes along. And so those 100 calcium ions go out and then they go back in. They go out and they come back in. Now let's say epinephrine comes along. And now let's say you get 200 units, 200 calcium ions that come inside the cell from epinephrine. Now what's going to happen, there are calcium pumps that pump the calcium into that chamber, and calcium pumps that pump calcium to the outside. Let's say 100 of these go in here and 100 go out here. Now on the next contraction, 200 are going to come out, and now you're going to get greater contraction. Make sense? Now what's going to happen, let's say that contraction is over. Okay? Now what's going to happen, 200 are going to come out. Now what's going to happen, just like normal, the normal 100 are going to go back in, but now 50 are going to go out that are left over, and 50 are going to go back in from the extra. Make sense? Now you're going to have 150 in here, and on the next contraction, now 150 are going to come out. Now the normal 100 are going to go in, 25 are going to be pumped out, 25 are going to be pumped in. Now you have 125 in there. So once epinephrine goes away, the situation is going to slowly go back to normal. Make sense? And that's what epinephrine does. It doesn't keep the response going all of the time. Okay? So that's how epinephrine gives you greater contractility. So now let's give names now to things. If that makes sense, we're going to start naming some of these proteins. But I don't want to give you the names if they don't make sense, because it's pointless. Okay? So let's name some of these proteins. Let's get this calcium out of the way. So what I'm going to do, I'm going to move this protein to the side here so we can name. There are two proteins here. The protein that actually does the blocking. The protein that does the blocking here, this protein right here, I'm going to make it black. This protein that does the blocking, this protein is called tropomyosin. T-R-O-P-O, myosin. So the tropomyosin blocks the binding sites on actin. It blocks those binding sites on actin. And the protein beside it that actually binds to the calcium and moves the tropomyosin out of the way, that protein is called troponin. So troponin is a calcium binding protein. It binds to the calcium and then it kind of twists itself to move the tropomyosin out of the way. Now you can get contraction. And so you have to think there are lots of these tropomyosin proteins covering all of those actin binding sites. If you get a lot of calcium, you're going to move a lot of them out of the way. You're going to get a really, really strong contraction. But if you don't have a lot of calcium coming out of the cell, then you're not going to move a lot of those tropomyosins out of the way, and you only get a weak contraction. Sympathetic output will cause more calcium to come into the cell, and if you have more calcium into the cell, you're going to move more tropomyosin molecules out of the way, and that's going to lead to a stronger contraction. Does that make sense? Excellent, excellent. You all are very, very good students. Now, let's talk about, so we know how the trigger calcium comes in. We know how you release your calcium spark. We know how the calcium spark goes back. how do we get rid of how do you get the cell back to its non-polarized state? So we've depolarized the cell. How do you get it back, to a polarized state? So what we need to do, several things have to happen. When all of these ions, all of these cations come into the cell, we make the cell very positive. The cell is going to be very positive. So we want to reduce the positiveness of the cell. It has a lot of plus charge on the inside. Let's see. So I'm going to do something with this calcium spark here. Just going to move this down just a little. It can still stay here. All of this is the calcium spark. Okay, so let's make the cells not so positive. So let's get rid of a few ions, some cations. Let's put some cations on the outside. So here we have So what would be a good cation to throw outside of the cell? Anybody have any idea? There's no way you would figure that one out. So sodium comes in, so let's push out something else that has a positive charge. Let's push potassium out of the cell. That way the cell won't be so positive on the inside. Now it's time for the cell to relax. And this is what I was talking about earlier. To your question, Turo. Okay. Now, there's calcium. Trigger calcium came in. Let's get rid of that trigger calcium. Now the cell is ready to relax. We've had contraction, ventricular contraction. Now during ventricular relaxation, we need to get rid of that calcium, the trigger calcium, so it'll be ready for the next time. So we have another protein here. And this protein is going to be a pump. Okay. And what this protein is going to do, it's going to take that trigger calcium, or calcium, whatever calcium it can find, it's going to take that calcium and pump it to the outside, so that the cell can relax, so that the ventricular cell can relax. Does that make sense? Why it needs to go back outside? Because it needs to be there so it could rush back in for the next contraction. Make sense? And you want to get rid of it because you don't want to be sparking. You don't want to be triggering those sarcoplasmic reticula when you need to have diastole taking place. So that's one way we get the calcium out. And this protein here is called a calcium ATPase because it uses ATP. It uses ATP to pump that calcium outside of the cell. That's one way to get rid of the calcium, but there's lots of calcium in the cell, and we need to get rid of some more calcium. Okay, so then we're going to have another pump here. This pump here is going to also push out calcium. It's going to take calcium. Remember, now the heart needs to relax, so we need to get rid of all of this calcium. But it's going to do two things. It's going to push calcium out, and it's going to do something that's kind of stupid. It's going to also bring sodium in. So we call this the calcium sodium exchanger. So it pumps calcium out and it brings sodium in. So we've kind of fixed the situation. The situation is kind of fixed now, except remember we have lots. Now we have potassium outside. So we brought calcium in and then we took calcium out. So calcium is okay. We brought sodium in, good. And we brought sodium in. So we have lots of sodium in. So we need to do two things now. We need to bring the potassium back in, and we need to take the sodium out. Make sense? And so now we have our last protein. Our very last protein is going to take care of both of those for us. This last protein is going to get everything back to normal. And so what it's going to do, it's going to take the sodium and push the sodium outside, and it's going to take the potassium and bring the potassium back inside. Now we're back to the beginning. We're back to our normal situation. So, during systole, when it's time for the ventricles to contract, the AV node is going to send out an electrical impulse. It's going to cause this cell to depolarize. Sodium is going to rush in. These calcium channels are going to sense that, allow calcium to come in. That's the calcium trigger. That calcium trigger is going to activate those calcium reservoirs, and they're going to release their calcium. They're going to release the calcium spark. That calcium spark is going to then, I guess I should say this. That calcium spark is going to then go to the troponin, cause troponin to cause tropomyosin to release. Then you're going to get contraction of the heart cell. And so the heart is going to contract. Now it's time for the heart to relax. So there are going to be pumps to pump this calcium back into the reservoirs. And there's going to also be pumps to pump the calcium outside of the cell. So the calcium is going to be pumped outside. Now, during systole also potassium was pumped outside. So now what you need to do is get the sodium, get things back to normal. So the calcium is going to be pumped out here, and the calcium is going to be pumped out here by the calcium sodium exchanger, but sodium is going to come in. Now we have a situation where there's too much sodium on the inside, too much potassium on the outside. And so this last pump, the sodium potassium ATPase, is going to pump the sodium outside, pump the potassium back inside. Now we have diastole, now relaxation. Now the AV node sends another signal, and the process goes on and on. It just keeps taking place. And that's how you get contraction or systole and relaxation, diastole of a heart cell. If you want to increase the amount of contraction, then you just give epinephrine. Then when epinephrine comes, it's going to put more calcium into the cell. Now you're going to end up with greater ventricular contraction. Does it all make sense? Exactly. Diastole is when the ventricles relax. I guess I should have put that somewhere. Her question was, diastole is relaxation, and my answer was yes. I don't have any room to write this here, so I'm going to put it on this page somewhere. So systole is contraction, ventricular contraction. And diastole, and that's an E, is ventricular relaxation. So during systole, calcium is coming in. During diastole, calcium is coming out. So anything you can do to increase the amount of calcium in a cell is going to lead, in a heart cell, is going to lead to greater contraction. And that's what the sympathetic nervous system does. That's what epinephrine does. It increases the amount of calcium in the cell, so you can remove more of the tropomyosin from the actin. Any questions? Any questions? Okay, I'm going to stop there.